Hello explorers, and welcome to the next part of the Convolutional Neural Network series. Last time I went into machine learning technique. I translated the multi-layer perceptron into Java code from a C library on the network. And the result of that was somewhat lacking. I didn't get it to work with Minst, and I really wanted to work with this quite standard machine learning example that is pretty much a hello world for machine learning, where you have a lot of different numbers that is handwritten, and then you train a network to actually find these numbers. So you have a set of numbers and a set of pictures and a set of labels for these pictures. And here we have a demo for this ConvNetJS. So this is a convolutional neural network written in JavaScript, which I think is quite interesting, and it has a lot of bells and whistles on it. It's not made for performance, so the author of this library actually says that if you want to do a network that is huge, a very large network, you should not use this library. This library is just for testing purposes and understanding neural networks. I thought that this was a good library to get into and do some translation and try to figure out how this works, and perhaps do some cleanup later on and find another structure that works better for Java. But I wanted just to start with a little bit of a demo here. So here we have a network that has been running for a while. I have ran it for 200,000 iterations, and at the moment it actually has a validation accuracy of 1. So every one, or 0.99 or 98, so it's quite good at actually finding the right values. Perhaps this network is too well trained, could be, but as we see by this curve here, the loss or the difference between the actual numbers and the right one is getting much better over time. So this curve is pretty much at the bottom at the moment. And this neural network is just an input layer, a convolutional layer, a pooling layer, and convolution layer, pooling layer again. And then I forgot to say, after this convolutional layer, then you have this this ReLU. Don't remember the name of that one. It's local response normalization layer. Quite interesting name for that one. And then we have a softmax layer, and we have this network. We create our layers and we train our network. And down here you can see what happens in the different layers. You have an input, and you see which different activations goes into this input layer. It's pretty much an in-out. And then you have the convolutional network, where the different activations for the different filters are. And then we have this I forgot it again. Local response normalization layer. Phew, I will never remember that. And this layer has makes it go back to it normalized the result from the earlier. And then we have a pooling layer that takes the upper one and makes shrinks the image, so you have less data in the layer. So you go from a large data set and then shrink it down in order to get less data to work with, and because most of the subtleties have already been found in the overlayers, so then we can shrink it down and do a more in-depth search on activations on a smaller scale, because we have already activated the differences in the large pictures. And then we do it again with another convolutional network, local response normalization layer, and a pooling layer again. And then we have this FC layer. I didn't see this up here. After the pooling layer they have an FC layer. I wonder if they have added that. And then you have this softmax layer. Might be that this FC layer is added in the function. I don't know. We have to look into that more when we translate. But down here we have the actual predictions that comes in, and we see that it's pretty much sure about what it sees. It doesn't have that many failures, which is good. Then again, it has been running for quite a while. So let's go to the code. Let's look at this first here. Here is the Java code that we saw earlier. First off, they set a lot of state. For some reason they wanted to have the class names as strings. Could be interesting to have in our Java application as well. They have the name the data set with a name. I am not sure if that is required either. They put a number of batches, so that's how many batches should be the training batches. And then they say which batch of the batches are the test batch, which I think is a bit strange, because when to get this missed, you often get 50,000 numbers, that is your training set, and then you get 10,000 that is your actual test batch or test file, so test set. So in this case it seems like they take 3,000 times 20 with 21, which is, let's see, 63,000. So they have a bit more training data than, or I think maybe the training data was 60,000 plus 10,000. Then it makes sense that they have the first 60 plus a little bit more. So they have probably merged these data sets then. A bit weird, but then again. Then they say that the dimensions of the images is 28, which they are. They are 28 times 28 pixels big, and then you have the image channels, one image channel. It's just white or gray or black. So we don't have the different color channels, and that's actually used for the depth in the input vector or the input layer. So, and then we have some booleans here. I don't know what they are used for, but if you look down here at the input layer, they actually have 24 times 24 instead of 28, and a depth of 1. So this cube they were working with here is a bit smaller than the actual image data, and that's because they actually create a window into the data at random to make the data less precise, because they don't want to take the perfect image. They want to take a bit of the image and still be precise. I'm not sure if that's a way that we want to go, but I kept it this way at the moment. And then they actually have this convolution network and an activation network for that convolution, pooling network, convolution again, activation network, pooling, softmax. And then they have a lot of different numbers here. I guess it's 8 filters. I don't know what SX stands for in this case. The stride is how much the window is moving. The padding is how much space, how many pixels you should put around the images. And on the softmax, you define the 10 numbers you can get out. So most of these input data is defined in a way that you can read them. They are readable, but I don't really know what SX stands for, but we will figure that out while building. And then we have this code that creates the layers. We have a trainer. Ada delta is the method for training, and they said that that was the easiest one to understand and implement, so I'm sticking with that one, or the easiest one to get a good result as well. And then they give it a batch size and the L2 decay, which should be a small number. I think they said that you could start with 0.1 and then make it smaller if you like to. In this case, it seems that they just set a value for it. So this is the code that I started with today, and that I wanted to make into Java code as much as I understood it. And because we have Java, which is a type-safe language, and it's required that we actually create types for different things, and I thought I didn't see why we needed to make these definitions. So I looked into this network here, and when they create the network, it's a lot of code for make layers. They look at if you have any definitions. They have a desugar method that goes into and looks at the different inputs and makes a softmax to an FC, and then they take a convolution or an FC and or is it that they push an extra definition of FC after a softmax? Let's see here, definition, new definition, softmax. Yeah, so they push an extra definition of FC. That's why I didn't see this FC. Interesting. So we need an FC layer as well before the softmax. And then they look at convolution, and if you have a convolution and an activation of this local response normalization one, then let's set a bias preference for that layer, and I actually set that inside of the class. Might be that we have to define that in some way, so we know if we have a specific activation, but I put it this way at the moment. And then if you have any of these, then you just push this definition here, so that is unchanged. So that's pretty much it. And after all of this, they set some input values from the definition and then create the different global objects. So this function does a lot of things, but nothing that is really required, I think. Might be that you want to make it easier for yourself, that you don't have to specify this FC or something. But I thought that I should take this function and create a more specified list. So you have to specify more in Java, but I think that's good enough. And then we have some small function here that calls a forward. We have something that gets loss, backwards. We get some parameters and grants. And I thought that that was some sort of result. And we make a prediction. And then we have some JSON functions. So that's what I looked at first, to get a feel of how the network is made up. I also looked at this layer input just to see how the inner function were set up. And then you have this forward function that get a V, which is an in activation, out activation value, or volume, which they call it. And you also have a boolean that says if this is in training or not. And then you have a backward that does nothing, but I saw that it also could return a value. And then we have this result function that returns a list or an array of the actual parameters and gradients. So I looked at these values, and you might be wondering why I went into depth and trying to figure out these kind of things. And that's because when I then go into looking at my Java, I actually find out that in order to build this in a good structure, I think, then I wanted to make an interface for this layer and say that I have a forward function that takes a volume. I called it a data block. So I have some data that I propagate through my network as a data block. And I also say if this is in training or not. And then I have this backward function that might return a value here. So I don't know yet if I need to return a value here. And then I have this back propagation result. So when we run this back, we get the result. And then you have a different function to get the result. I don't know if this is a good structure, but that is pretty much what the other code told me. So then I have all these different layers that we were looking at before. We have the input layer, for instance. And in this case, I just set it up that I return an empty result, and the other function doesn't do anything at the moment because I just wanted to create a structure. And I set the specific inputs that this definition were setting in the example. So that's pretty much it for these layers. The data block, I found that you had an SX and SY, a depth to get the size of the data block, and then you have an array of weights and another array of different weights. They just call it DW. So in the future we might change these names to make them more readable and understandable, but I want to keep it in the way that they have defined it in the other library to for easy translation. And then we have this mist test, which is the actual void main function, where I just started with copy pasting in the actual code from the HTML example we looked at earlier. So from this first HTML file, I just copy and pasted this in, and then started to translate it into Java code. So we have our array of strings in start. We have the dataset name, all these hard-coded values, which I don't know if we need them in this manner, or if we have to set them in some loader, or how we will use these. And then I created a layer array, which has the interface of layer, and then I put my different layers inside of this array. So we have the input layer with the parameters we saw, we have a convolution layer with the parameters, local response normalization layer with each parameters, and I didn't see that it actually had any parameters. You can go back and see in the this one, when we define this, it just has the type relu, so it doesn't have any other parameters to it. And this FC has number of neurons, which is the same as number of classes. So this one we need to translate as well. And so we can put it here so we remember that. And then we have the pooling layer, convolution layer again, and local response normalization, pooling. And now we have this FC and softmax layer. I create a Java object which does nothing, then takes the layers. So they had a net object that had all the layers. I'm not sure that we need a specific object to hold the layers, because the layers seems to have all the data in them. So I'm not sure if this will add any functionality. I guess that the net does the back and forward function, so it might be required. But yeah, I give it all the layers that I have created, and then I created this trainer interface and a class that takes all these values and just sets them inside of the class, just so we have some sort of a structure here. And then we need this FC as well. So what could FC stand for? Let's do some investigation. We need to create this strange class of FC. So let's go into probably not a normalization layer, it's not a pooling layer. We had a lot of layers here. Think they are in can look into non-linear. That's the reload layer. We can look in here as well. So here we have the FC, which is a fully convolutional layer. So that's a fully connected layer. So let's create a fully connected layer as well, because I like to have the fully connected layer, which takes number of classes or number of neurons. So let's see here. In the layers, we create a new other class, fully connected layers. It will implement the layers. Just write the correct definition later. Need one just put everything in here and change this to number of neurons. Nope, sorry. Fully connected layer. This is the one that I wanted to change. Yeah, it was the right one. I just didn't change the name of it. So now I have created this fully connected layer as well. So this means that I have translated all the code as I can see it from the main class into Java. And I think that in the next video I will try to translate some of these layers. So I will take it layer by layer, and then we will take a look at the trainers, because there are a lot of different trainers. So I like this setup that you have all the layers as different classes, and then you have trainers as different classes, you have data as different object as well. So yeah, it seems very modular and nice to work with. So I'm looking forward to doing some more work with this. And yeah, I hope to see you in the next video.